Back. Long day after today I will discuss about ring theory again. Today I will introduce reducible and irreducible elements of a ring. This topic is very important for any competitive exam. So I will highly recommend you please see today's video with pay attention. Reducible and irreducible element of a ring is, let R be a commutative ring with unity 1. Then P be a non-zero non-unit element of the ring R. Then P is called irreducible element if for every AB belongs to R, P is product of these two elements where either A or B is unit. P is called reducible if P is not irreducible. Are you getting? Well, for example, consider the set of integer and consider the element 7. Obviously, in J, 7 is not unit and 7 is non-zero element of the ring Z. Then we can write 7 as 7 times 1, which is also write as 1 times 7. So, obviously, 7 is an irreducible element of Z. We can write 7 as minus 7 times minus 1. So, obviously, not only 7 is an irreducible element of integer, plus minus 7 is an irreducible element of integer. Okay, to 7 is also prime element of Z, because if we consider two element AB belongs to Z such that 7 divide AB, that imply either 7 divide A and, sorry, here not and, or 7 divide B. So obviously 7 is a prime element of integer. Actually in Z, if P belongs to Z, where P is a prime number, then P always irreducible element as well as prime element. Okay? Consider composite number 10. We can write 10 as 10 times 1, also 1 times 10, also 2 times 5. So, we all of us know in Z only units are plus 1 and minus 1. So, here neither 2 nor 5 is a unit of Z. So, 10 is not irreducible element of integer. In Z, when element P is a prime number, so P is irreducible element and as well as prime element of integer. Are you getting the idea of reducible and irreducible element? Now consider other type of set of Gaussian integer. We all of us know set of Gaussian integer contains the unit element 1, minus 1, I and minus I. Here, if you consider the element A equal to 1 plus I, then this is irreducible element of Zi. Now let's see how the element 1 plus I be irreducible element in Zi. All of us know in Zi the element are look like A plus IB, where AB belongs to integer. First I will check is the element 1 plus I is an unit element of the ring Zi. For this, multiply 1 plus I with an element of Zi, and to prove 1 plus I is an unit element, this is equal to 1. Then from this expression, I times A plus B equal to 1 minus B minus A. Here notice this part is imaginary part and this part is real part. So this equality cannot possible. That means the element 1 plus I is not unit element of Zi. Okay. Also the element 1 plus I is a non-zero element of the ring Zi. We have to prove 1 plus I is an irreducible element of Zi. So to prove irreducible element, consider 1 plus I equal to product of two elements in Zi. Consider this is A plus IB times C plus IB, where A, B, C, D belongs to integer. Similarly, since 1 plus I is an element of Zi, similarly 1 minus I is an element of Zi. So write 1 minus I and consider this is product of two elements A minus IB times C minus ID. Similarly, A, B, C, D belongs to integer. Now multiply equation 1 and 2. Then this would be 1 plus I times 1 minus I equal to A plus IB times A minus IB times C plus ID times C minus ID. Then that imply 2 equal to A square plus B square times C square plus D square. And from this expression we can write either A square plus B square equal to 1, then obviously C square plus D square equal to 2. When A square plus B square equal to 1 and C square plus D square equal to 2, then that imply A plus IB is unit in the set Zi. A plus IB is unit in Zi because A square plus B square equal to 1 means either A equal to 0, B equal to 1, or B equal to 0, A equal to 1. Case 2, when A square plus B square equal to 2 and C square plus D square equal to 1, then from this expression we can write as easily C plus ID is an unit in Zi. Okay? C square plus D square equal to 1 imply this is possible either C equal to 0 or D equal to 1, or D equal to 0 and C equal to 1. Either A plus IB or C plus ID be the unit element of Zi, So obviously 1 plus I is an irreducible element of Zi. Are you getting the idea? In Zi, if we consider the element A equal to 2, then notice 2 can be written as in Zi 1 plus I times 1 minus I. And neither 1 plus I nor 1 minus I is unit element of Zi. Okay? So, obviously 2 is not irreducible element of Zi. Now in Zi, if we consider the element A equal to 5, then we can write 5 equal to 2 plus I times 2 minus I. And neither 2 plus I nor 2 minus I is an unit element of Zi. So, in Zi, if we consider the element A equal to 5, then this is not irreducible element. 5 is not prime element in Zi because 5 divide 2 plus I times 2 minus I. Here B equal to 2 plus I and C equal to 2 minus I. But 5 does not divide 2 plus I or 5 does not divide 2 minus I. So 5 is in Zi not irreducible element nor prime element. Are you getting the idea? Well, in Zi, if we consider the element A equal to 3, in Zi obviously 3 is non-zero element and non-unit element. Then to prove 3 is an irreducible element of Zi, consider 3 equal to product of two element of Zi, similar to before, A plus IB times C plus ID. If we apply mod both sides, then this would be 9 equal to A square plus B square times C square plus D square. And we can write 9 as 9 times 1. So case 1, when 9 equal to 9 times 1, then that implies A square plus B square equal to 9 and C square plus D square equal to 1. And from this expression, that implies C plus ID is an unit element of Zi. Okay? Because C square plus D square equal to 1 means similar to before. C equal to 0, D equal to 1 or D equal to 0, C equal to 1. Finally, we can write 9 equal to 1 times 9. So case 2, from this expression, A square plus B square equal to 1 and C square plus D square equal to 9. And from this expression, that implies A plus IB is unit element of Zi. Okay? Finally, we can write 9 as 3 times 3 and case 3, for this expression, A square plus B square equal to 3 and C square plus D square equal to 3. And in Zi, this equation cannot possible. Have you understood? This expression cannot possible. Therefore, for the element a equal to 3, either a plus ib is unit in Zi or c plus id is an unit element of Zi. So, in Zi, the element 3 is an irreducible element. Now I will see some shortcut method to find the irreducible element in Gaussian integer. X equal to a plus ib with the element of Zi where a not equal to 0 and b not equal to 0. If a square plus b square equal to p where p is a prime number, then x equal to a plus ib is an irreducible element in Zi. Second formula, x equal to a plus ib belongs to Zi where either a equal to 0 or b equal to 0. Then if absolute value x equal to p where p is a prime number and if 4 divide p minus 3, then x equal to a plus ib is an irreducible element in Zi. For example, consider x equal to 7. Here a equal to 7 and b equal to 0. And 4 divide 7 minus 3. So, obviously, the element 7 is an irreducible element in Zi. Are you getting the idea? Oh, it's a new type of set. Here the ring is z square root of minus 5, which is actually set of those elements which is look like a plus b square root of minus 5 where ab belongs to z. And this ring is actually the subset of complex number. I will prove 2 is irreducible element but not prime element. While 2 is a prime element of the set, consider a equal to 1 and b equal to 1 for simplifying. Then obviously notice 2 divide 1 plus square root of minus 5 times 1 minus square root of minus 5. And 2 divide this part because 1 plus square root of minus 5 times 1 minus square root of minus 5 equal to 1 plus 5, which is equal to 6. Consider this term as b and this term as c. Now to check the prime element, we have to prove if 2 divide bc, then either 2 divide b or 2 divide c. Let's consider 2 divide b. If 2 divide b, then that implies there exists an element x plus y square root of minus 5 in the ring z square root of minus 5 such that 2 times x plus y square root of minus 5 equal to 1 plus square root of minus 5. And from this line it implies 2x plus 2y square root of minus 5 equal to 1 plus square root of minus 5. This line it implies 2x minus 1 equal to 1 minus 2y times square root of minus 5. That implies 2x minus 1 over 1 minus 2y equal to square root of minus 5. And this is not possible because this is the member of rational number, but this is not rational. So this equation cannot possible. That means 2 does not divide b. Similarly, we can prove 2 does not divide c. That means the element 2 is not prime element. Now I will check, is the element 2 is irreducible element? 2 is not an unit element because 2 times a plus b square root of minus 5 equal to 1. That implies 2a plus 2b square root of minus 5 equal to 1. And from this line, this is true, 2b times square root of minus 5 equal to 1 minus 2b. Here, right hand side is integer and left hand side is not integer. So, 2 is not unit element. Also, 2 is non-zero. To find the irreducibility, consider 2 is written as product of two non-zero element a plus b square root of minus 5 times c plus d square root of minus 5. Now, take the conjugate both sides, then this would be 2 bar equal to a minus b square root of minus 5 times c minus d square root of minus 5. Now multiply these two equations, then this would be 4 equal to a square plus 5b square times c square plus 5d square. And from this expression, we can write easily 4 equal to 4 times 1. So, case 1, consider similar to before, a square plus 5b square equal to 4 and c square plus 5d square equal to 1. Also, we can write 4 equal to 1 times 4. So, for case 2, that from this expression we can write a square plus 5b square equal to 1 and c square plus 5d square equal to 4. Finally, we can write 4 equal to 2 times 2. So, case 3 imply a square plus 5b square equal to 2 and c square plus 5d square equal to 2. From case 1, c square plus 5d square equal to 1. From this line, it implies c equal to plus minus 1 and d equal to 0. And that means c plus square root of minus 5d is unit for this expression, case 1. For case 2, here a square plus 5b square equal to 1. That means for this expression, a equal to plus minus 1 and b equal to 0. That means a plus square root of minus 5b is unit. And this equation, a square plus 5b square equal to 2 and c square plus 5d square equal to 2 cannot possible. That means if we can express 2 as a product of two elements a plus b square root of minus 5 times c plus d square root of minus 5, then either a plus b square root of minus 5 will be unit or c plus d square root of minus 5 will be unit. So obviously 2 is an irreducible one question which had come in GATE 2018 exam. The question is, consider the ring Z square root of minus p equal to set of all elements a plus b square root of minus p, where ab belongs to integer. Then the element 2 in Z square root of minus p is option 1 unit, option 2 square, option 3 prime and option 4 irreducible. This is very easy type question similar to before. Let's check again this question. First I will check, is the element 2 is unit in the set Z square root of minus p? To check unit, then 2 times a plus b square root of minus p equal to 1. That implies 2a plus 2b square root of p times I equal to 1. And from this expression, 2a equal to 1 and 2b square root of p equal to 0. And from this line, it is true a equal to half and b equal to 0. But notice, here ab belongs to integer, but here I have got a equal to half. That means if the element 2 is unit, then it will break the condition. That means 2 is not unit. That means option 1 is a wrong option. Our second condition, 2 is a square element. For this, consider 2 equal to a plus b square root of minus p whole square. That implies a square plus b square times minus p plus 2ab square root of minus p. And from this expression we can write a square minus pb square plus 2ab square root of p times I. And from this equation, it is true a square minus pb square equal to 2 and 2ab square root of pi equal to 0. And from this expression, that imply ab equal to 0. And ab equal to 0 imply either a equal to 0 or b equal to 0. And notice, if we consider b equal to 0, then a square equal to 2, that implies a equal to plus minus square root of 2. But here ab belongs to integer, so this will break the relation. If we consider similarly a equal to 0, then that implies b square equal to minus 2 over p, who is not belongs to integer. So this is also break the relation. So 2 is not square element. Okay, that means option 2 also wrong option. Now I will see, is 2 is a prime element? Here the element is look like a plus b square root of minus p type. For simplicity, consider p equal to minus 5, a equal to 1 and b equal to plus minus 1. Then the element c equal to 1 plus square root of minus 5 and d equal to would be, just put the value, this would be 1 minus square root of minus 5. Then cd would be 1 plus 5, which is equal to 6. Therefore, obviously 2 divides 6, but 2 does not divide 1 plus square root of minus 5. Also, 2 does not divide 1 minus square root of minus 5. That means the element 2 is not prime element. Are you getting? Option 3 also wrong option. Now I will check, is the element 2 is irreducible? Obviously irreducible element, because the proof is similar type of proof. Just check again. Here consider 2 is written as product of two element a plus b square root of pi times c plus square root of pi, because here given in the question the element are look like a plus b square root of minus p. Now the conjugate of this equation would be 2 equal to a minus b square root of pi times c minus d square root of pi. Now multiply these two part, then this would be 4 equal to a square plus b square p times c square plus d square p. And from this expression we can write easily case 1, a square plus b square p equal to 1, c square plus d square p equal to 4. And from this expression, obviously a plus b square root of pi is unit element. Also, case 2 would be similar to before. This part I had discussed many times. So, just look. Case 2 would be c square plus d square p equal to 1 and a square plus b square p equal to 4. And from this expression, minus d square root of pi is unit. And case 3 is a square plus b square p equal to 2 and c square plus d square p equal to 2. But this expression always cannot possible. So, case 1 and case 2 possible. That means, in this equation, we can write 2 as product of these two elements. Then either this would be unit or this would be unit. That means obviously the element 2 is an irreducible element. Today I will stop here, but I will highly recommend you please see today's video with pay attention, because these type of questions are very important for any competitive exam. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.